Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Farhad Ali, your instructor for the course of Theory of Fluid. This is your third online lecture. I hope you will find this lecture in very good health. Okay, so this is the basic. We are already discussing the basics of Theory of Fluids. This is the continuation of the previous lecture. In the previous lecture, we have classified the fluids into real and ideal fluids, or you can say the envisaged fluids and the real fluids. And again, the real fluids, if you look at the flow chart, look at this flow chart. Again, the real fluid is divided into Newtonian and non-Newtonian fluids. Okay, so these actually this is the main two types of the real fluids. So we will discuss this as we are already discussed the real fluid and envisaged fluid. So now we will discuss the Newtonian and non-Newtonian fluids, very important fluids. So you can see Newtonian fluid or Newtonian viscous fluids are those fluids in which shear stress is directly and linearly proportional to the rate of deformation. Okay, shear stress is directly and linearly proportional to the rate of deformation are the fluids which obey the Newton's law of viscosity are called Newtonian fluids. Okay, so we can define the Newtonian fluids or Newtonian viscous fluids in which the shear stress is directly and linearly proportional to the deformation rate. Are we in the simple words, we can say that those fluids which obey the Newton's law of viscosity. So what is Newton's law of viscosity? The Newton's law of viscosity is that shear stress is directly and linearly proportional to the deformation rate. Before to discuss the mathematical form of this statement, or to express this statement in the mathematical form, let me discuss this what are shear stresses. So though it is a separate lecture, and we will have a separate lecture on shear stress or shear stresses. So we have two kind of stresses. One is called the normal stresses, and the second one is the shear stresses, or also we call this the tangential stresses. Remember, okay, that normally there are two types of stresses. One is called normal stress, and the other is called shear stresses or tangential stresses. We also call this tangential because these stresses are tangential to the surface, parallel to the surface. And what we call deformation, actually deformation is a shear strain. We call this deformation, or we also we can say this like the shear stress is directly and linearly proportional to the shear rate or shear strain. Okay, or we call this shear rate. So when we apply the shear stresses or tangential stresses, shear rate or shear strain uh, is produced. What is the shear strain or rate of shear? We call this deformation. Okay, so when you apply the stresses and the or in other words tangential stresses, because stresses, okay, shear stresses are tangential stresses, and these stresses have a relation directly and linearly with the shear rate or the deformation. So we call such fluids as a Newtonian fluids. And if we discuss this, how these stresses are produced or generates, so actually um, stresses are produced due to the viscosity. As we already discussed, the viscosity, this is actually the internal forces are the resistance to the flow. So when these uh, resistance forces generates due to the flow of motion, so at the same time stresses are produced. So as already I discussed that stresses are normal and tangential. So those stresses which are perpendicular to the surface are called normal stresses, and those which are parallel to the surface are called tangential stresses. Okay, so uh, the flow causes due to the shear or tangential stresses, not due to the uh, normal stresses. So as I already discussed that we have a separate lecture on this, but uh, very briefly I just discuss that how uh, these stresses are produced. Okay, so okay, so once when we have a surface, for example this is a surface, okay, and we have considered a very small, okay, a very infinitesimal point here, and the area of this point is del A. Okay, so two kind of forces will acting on this point, on this very infinitesimal, very small area. One will be called F. This F, look at this one, and the other will be in this normal to this uh, point. Okay, we call this normal force. So if you look at this one, the force we have, uh, we know this, and this will be a very small force. We denote this force by del F. Del F means a very small force. Okay, so if this force del F acting on a very small area del A, and this del A tends to 0. Okay, so normally we call this pressure. Okay, you remember that F by A, force per unit area. So if this is this force is acting normally or perpendicular to this area, so we call this a normal stress. Okay, so it means that pressure is also represented by the forces per unit area, the forces which acting on the area. But we now uh, denote this by this uh, sigma. We call this, then we call this a normal stress. And also at the same time, there are some forces which will be acting parallel to, uh, we call this tangential force, Ft, which is acting parallel to the this area, this small area. Okay, so this force, this relation, that tangential force which is acting parallel to the point of to this point, okay, we call this shear stress or tangential stress, and we denote this by from this tau. So tau represents the tangential stresses and sigma represents the normal stresses. And we will discuss this, the difference between the pressure is only, and the stresses. Pressure is only acting perpendicular to the area, but stress is acting perpendicular to the area as well as tangential to the area. So this is the difference between the two. Okay, and the second difference between the pressure and the stresses, that stress is always produced when the fluid is at rest. For example, if this area, this is the area and there is a fluid, and the fluid is at rest, so then there will be pressure. But the fluid is at rest, have zero stresses. Stresses only produce due to the flow of motion. If there is a fluid and this fluid is at rest, so there will be no stresses, but the pressure exists. So this is the difference between stresses and the and mm, pressure. And also you know that pressure is actually a scalar quantity. Okay, and okay, and you know stresses are the high rank of vector. Okay, so this, I just discussed this, that how stress is produced. So when the force is applied tangentially or perpendicularly to this area, so it produces stresses. Okay, so those stresses which is parallel to the area, sorry, normal to the area, are we call this uh, normal stresses, and those which is tangential to the area, we call this is actually normal, in the normal direction. Okay, and these are parallel to the area, so we call this shear stresses. So the fluid's motion causes due to this shear stresses or tangential stresses. Okay, uh, these stresses are responsible of the deformation of the fluid or the motion of the fluid. Okay, so That's why I have discussed that how what are shear stresses. So actually, shear stresses uh, generates develops due to the viscosity, and viscosity is actually as a resistive force. So it is again same like the pressure. It generates due to the forces acting per unit area, but these forces acting perpendicular to the area and tangentially to the area. So due to this, we have uh, divided these stresses into tangential stresses and shear stresses. Okay, so um, again, uh, if we describe the fluid that classify the fluids, okay, so those fluids uh, in which the shear stress is directly and linearly proportional to the rate of deformation. Okay, the deformation or the change in shape actually because of these stresses, because of this force. If if the relation between these two is linear and also proportional, so we call such fluids as a uh, Newtonian fluids. Are the fluids which obey the Newton's law of viscosity are called Newton fluids. So, what is actually the Newton law of viscosity? And we will derive this Newton law of viscosity, this relations. That again, it is actually nothing, but this is the mathematical statement of this uh, theoretical statement that these are the shear stresses, and the shear stresses are directly proportional to the deformation. So we call this the deformation, okay? And we will develop this relation, okay? That how this relation actually develops, and as you mentioned that the shear stresses, these are the shear stresses directly proportional to the deformation, because this is the mathematical form of deformation, that the the change in velocity occurs in the due to y-axis, okay, and while removing the sign of proportionality, uh, we can write this as a mu du by dy. Look at this property which we multiplied with this deformation, okay, and this property is actually is the constant of proportionality, and it is known as dynamic viscosity. We call this a dynamic viscosity, okay. So this is a constant, so means for the Newtonian fluids, all the fluids have this property constant, not changing with respect to uh, stresses, okay. While applying the stresses and deformation occurs, this property will remain constant. It is very important uh, property, and at this time you can easily distinguish the Newtonian fluids. And if you look at this one, it is quite interesting that I already mentioned that. Look at this one, the relation between this and this, okay. So when we applied stresses, this is called deformation. In Urdu we call this bigard, okay, the change in its shape. So when this is applied and the change occurs, the deformation occurs, this property will remain constant. And if it happens, if it satisfies, then such fluids are called the Newtonian fluids, or the Newtonian viscous fluids, okay. So if you look at this one, we can calculate this uh, property, okay, this constant of proportionality like this, Look at this one. We already said that these are the tangential stresses. Okay, what does it mean by when we discuss stresses? So we will explain this. What does it mean by this subscript x and y? Subscript x shows the plane in which the force is acting or the stress is acting, and y shows the direction in which direction the stresses are acting. Okay, so we will discuss this when we have this topic. So as we have mentioned this relation that and actually what is this relation? This relation is called Newton's law of viscosity, and I can write this du by dy. Okay, because this changes occurs in the y direction, so that's why we have this one. If this is occurs in the x direction, so this will be then x. So the change in velocity with respect to y. This u is velocity and this is xx. So if I write this, look at this one. Mu is equal to this tau xy. Tau x actually is the shear stress or tangential stress, and I already mentioned that the flow is already possible due to the shear or the tangential stress divided by du by dy. So if I define the viscosity, what is viscosity? As we have already discussed this theoretically, that it is resistive to the flow. It is a property which resists the flow. But look at this one. It is a constant. It is a constant property which is the ratio of shear stress and shear strain. Okay, look at this one. Or you can say that, okay, that uh, when we apply stresses, the relation of stresses with strain or shear strain or shear rate is called uh, this expression, this constant of proportionality, which we call dynamic viscosity. So look at the dynamic viscosity, that if you apply the stresses and deformation produces, and this property remains constant, so we call this such fluids as a Newtonian fluids. So you can also discuss the relation, or mathematically you can express the viscosity in this form, that it is actually it is the uh, the property uh, when shear stress is divided by its deformation, or the ratio of the shear stress with the deformation. Okay, it is not like such ratio, because it has because normally when we have a ratio, so for the ratio there is no dimensions, but this mu has dimension. So it doesn't mean that it is just like ratio. Okay, but I have just, this is versus shear stress versus deformation. Okay, and it produces a property which we call this property, this dynamic viscosity. Okay, and also from this we can derive its dimensions. We call this dimension. Okay, that the dimension of this divided by the dimension of the this term, and this is velocity, which has dimension meter per second, and the y dimension is meter. We call this length. Lt minus 1 is the dimension of the u, and the y dimension is L minus 1. And also we have how to find the dimension of this tau xy, as I already mentioned that tau xy is actually nothing, but it is force per unit area. So the force dimension is equal to F is equal to ma. So from ma divided by a, okay, which is L square. So you can, the dimension of this will be the dimension of F, okay, the force dimension, the dimension of force divided by L square t minus 1. So from this you can derive this, the dimension of this term viscosity, and we will derive this, the dimension of, okay, of this property. So uh, now uh, we can classify the fluid while using this property. Those fluid for which the viscosity does not change when you apply the stresses and the deformation occurs, but this property remains constant. So we will consider such fluids as a Newtonian fluids. Okay, but those fluids which do not have this property as a constant, while, in other words, while applying stresses, deformation occurs, but this property will increase or decrease. Okay, because this is viscosity. So the fluid will become thicker or thinner. So when you applied stresses, and in simple words, again I say that stresses are actually forces. Okay, so when you apply the forces on something and it deforms, and no change occurs in its thickness or in viscosity or its, okay, nature of its viscosity, so such fluids are called Newtonian fluids. Okay, so easily you can, and you can uh, classify the fluids. If you have a fluids in hand, so you can easily say that, you can say at the spot that the given fluids are Newtonian and which fluids are non-Newtonian. Okay, so this is very important property for this one. And also we have a graph for this. Look at this one, this is very important. I have, just like I have shown, that mu is equal to tau du by dy, and I have sketched the graph, stress versus deformation. When we apply force, deformation occurs. So look at this, is called a deformation, and look at this deformation is, okay, is a straight line as a linear function. Why we call this a linear? Proportion and linear. Look at when stress is zero, a deformation is also zero. Okay, but again, if I, when the stress is zero, deformation is zero, stresses are zero, but still there will be pressure. So that's why pressure is different from the stresses. Okay, so when we increase, let's say, when we increase the stress at the same rate, the deformation also increases. Again, when we increase, if we double the stresses, so double deformation occurs. So we call this proportional. Okay, that shear stress is proportionally related with the deformation. And look at this, this straight line. This straight line is called mu. So this mu is constant actually. Okay, this is mu. Okay, so now you can say that which fluids will be Newtonian. Okay, when we apply the stresses, deformation occurs, but no change occurs with viscosity. So we call this Newtonian fluids. Okay, so let me sketch this graph. the relation between the stresses and the deformation or the rate of shear. On the x-axis we have this deformation, we call this deformation. This partial derivative shows, or this derivative shows the deformation, and on this axis we have the stress, and actually this is the subscript. I have already discussed this for the stresses we have this one, that on which plane it is applying and in which direction it is applying. So this subscript shows the plane and the direction. Okay, so in this case the plane is x and in the y direction. Okay, so when we have zero stress and zero deformation occurs, but as we increase the shear stress, the shear strain or the deformation also increases, and you can see this dot. Okay, now if you increase this by this quantity, it has the deformation is also increased with the same quantity. And when you uh, connect join these dots, you will have a straight lines, and which I have mentioned it. What is this? This is actually mu. This is the viscosity, the dynamic viscosity, and for which we have this dynamic viscosity as a linear line, as a linear function. We call this Newtonian fluids. Okay, Newtonian uh, fluid. Okay, so now uh, I just give you example, okay, about the fluids. That if you have a fluid, okay, for example, we have a fluid in this glass, okay, there is a fluid. Maybe this fluid is water, let's say, and while using spoon or some stirrer, okay, and you shaking this fluid, okay, you are shaking this fluid, you are shaking. So what does it mean? Using your spoon, or that spoon is actually producing stresses, so you're applying the stresses. So while using your stresses, okay, stir this fluid which is inside this glass, and check its viscosity, checks its nature, that what is this nature before the stirring or before the shaking, and now what is its nature. Okay, so for example, in the case of water, if this is water, so if we check first its nature, uh, the nature of its thickness, okay, so you can use the spoon and check uh, its thickness, its concentration, and then after some time just shake this or stir with this fluid with the spoon again and again, and maybe after 5 minutes you just check its uh, thickness again. So what will be its actually now its thickness, which we call the viscosity. Okay, if this is water, inside this is water, okay, and this is water, okay? And you are using the spoon to stir this, and after some time you check that uh, the nature of this fluid again, that is it become thick or remain the same. Even you can check that to flow this water on the smooth surface. Check how it moves before the stirring, before applying the stresses, and after shaking or stirring this water inside this glass, and then try to allow to flow. So you will see that its velocity will remain the same, and no change will occur in its viscosity. It means that it will have the same viscosity. Its nature will be the same. It will not become thinner or thicker. Okay. For example, if you stir this and after some time it becomes like honey, the water becomes like honey, like it becomes very thick, and it is not easy to pour it from this glass, but before it was easy. So this will not be a Newtonian fluid. Okay. So very easy that water does not change its viscosity or its thickness while disturbing this water, or while stirring this water, or while applying stresses on this on the water. Similar example is of the ear. Okay, that when you disturb the ear, when you apply the stress, okay, and you shake the ear, if this is ear, inside this is now ear, okay, and you are disturbing, you are applying stresses, you are shaking this glass. It means the shaking means you are disturbing, and this means that you are applying stresses. And after this you just want to check, okay, so it will have the same nature, and its viscosity will remain the same. So such fluids are uh, Newtonian fluids. But there are many fluids which do not obey this property. Okay, for you, okay, you just take the honey. Okay, this is a mini assignment for you. Take honey in a glass and check, observe this honey in the glass before shaking. Okay, and then uh, take a spoon and with that spoon, stir the spoon inside the honey, okay, frequently for 1 minute, for 1 minute or 2 minutes, and then check the nature of the honey, that the honey becomes thinner or thicker while applying this stirring, okay, while applying the stress or applying disturbing with this spoon. Okay, so then send me your response or answer about the honey, that while we applying some stresses, are we applying the spoon inside the, we stir the spoon inside the honey which is in the glass, okay, or in the cup, and after observing, after stopping the stirring, just observe the nature. Is it become thinner or thicker? Okay, and if or it remains same. Okay, so if it remains same, so it will have this graph, and then it will be Newtonian. Otherwise it will not be Newtonian, means it will be non-Newtonian. Okay. Okay, so please do this. This is an experiment for you. Okay. As I have already discussed this, the Newtonian fluids in detail. So now non-Newtonian fluids, so which I have already discussed this, that those fluid which do not obey the Newton law of viscosity, or where the this relation is not linear, this relation is not linear, okay, uh, the fluids which not lie on this line are called non-Newtonian fluids, okay, we do not have the straight line, okay. So we call this the non-Newtonian fluid. We will not obey this relation. When you apply the stress, the the strain or the shear, the deformation will not be occur in the same uh, way, okay, or not in the same magnitude. So we call this the non-Newtonian fluids. Uh, Fluids which do not obey the Newton law of viscosity, that is, shear stress is not directly and linearly proportional to the shear rate, such as fluids for which the shear stress is directly proportional to the deformation rate in a non-linear manner. There will be not a straight line now, and we mathematically uh, express this. You can see the shear stress, we call the shear stress, and again I'm uh, uh, I say that don't confuse with this, because these are the stresses in which the substrate shows the plane and the direction. So don't it may be yx or xy. Yx means y plane in x direction, or xy means x plane in y direction. Okay. So now look at this one. This is proportional to the uh, deformation with power n, okay, and this n will not be equal to 1, because if this is equal to 1, so it becomes Newtonian fluids, okay, and n may be less than 1 or greater than 1 but not equal to 1, okay. So if you have, okay, uh, this relation in which n is greater than 1 or less than 1, so you can see uh, if you compare this with the previous one, so when we put n is equal to 1, so it will it will reduce to the same equation expression which we already used for the Newtonian fluids, okay. This n shows a non-linearity, so we can write this. Look at now for this, uh, the sign of proportionality, the constant of proportionality is k now instead of mu, okay, to differentiate this. Here, constant k is the consistency index, and S is the flow behavior index, okay. N is the flow behavior index. Okay, so K is, we call this consistency index, that how the fluid is consistent, and S is the fluid behavior index. So it shows that the fluid is Newtonian or non-Newtonian. When we k is equal to mu and n is equal to 1, if we put k is equal to mu and n is equal to 1, so the above equation reduces to the Newton's law of viscosity. Okay, and now uh, the second equation can also be expressed as this equation. Uh, this equation uh, can also be uh, can also be expressed as tau by x eta du by dy, where eta is equal to, when we put eta is equal to k du by dy n minus 1. Okay, so when we put here this one, and these are the product, so what do you have? Du by dy n minus 1 into du by dy 1 plus 1. So plus 1 and minus 1 will be cancelled, and just we will have n k. Okay, so there is nothing different between the previous equation, uh, this equation, and this equation. Okay, where eta is actually that we call this the apparent viscosity, which is okay, the apparent viscosity, apparently, which you can see the nature of the fluid. The okay, we call this the apparent viscosity, like toothpaste. You can see egg white, liquid soaps, ketchup, shampoo, some oils, biological fluids. So in the biological fluids, we can say that blood, okay, or some other fluids, okay. So some fluid which is inside the knee, also those fluids are called biological fluids. So uh, these are called the non-Newtonian. All these are the non-Newtonian fluids, and in this fluid the viscosity will not remain constant. Okay, for example, you can see in the toothpaste, if you apply the stresses, you will see that its viscosity will be decreasing. The after applying the stress, when you apply the stress by your finger, okay, so the paste uh, goes out from the tube, and you can see that its viscosity is reduced. That's why it starts motion. Okay, so similarly, you can see the ketchup shampoo while in the ketchup. Okay, while you apply the stress, okay, or you can stir with the spoon, so its viscosity decreases. It becomes thinner. Okay, and maybe some fluids will become thicker, while or maybe some oils will become thicker, not thinner, but while applying the stresses. So is the viscosity increase or decrease by applying the stresses? Such fluids are called non-Newtonian fluids. Okay, so look at this very interesting diagram, schematic diagram. You can see this. These are the shear stresses. This is the deformation rate. We call this the deformation rate, and you will see that we will prove this. This is the deformation rate, and you know that when we say the deformation rate, there is actually some the derivative with respect to time, but actually this has been derived from, yes, from the derivative with respect to time, the denominator. We will derive this term. Okay, so you can see this, that how the fluid has been classified. So look at this one. When the shear stress is applied and the deformation is like straight line, This means that the viscosity is constant, and we call this the Newtonian fluids. Okay. Also, some fluids are here. Okay. And look at this one. Those fluids which is not linear. Okay. So we have divided this into the dilatant fluids, pseudoplastic fluid, and look at the very special, the Bingham plastic fluid. Look at these fluids. Okay. Remember, those fluids which are which lies on this one. So what does it mean? The fluids which lie on this line. So what does it mean by the line? When something is on this line, so the deformation will be zero. Okay. So this means, okay, so something on this line will have this property zero. So what does it mean? That if you discuss this fluid being a plastic, initially it behaves like solid. What does it mean? No deformation. So when we say no deformation, look at this one. We increasing the shear stress, but the deformation rate is zero. No deformation occurs. No deformation. We increasing the stresses, but no deformation occurs. Look at this one. We increase, and when the stresses reach to this point, okay, when we increase the shear stresses to this level, then the fluids start motion, and this motion is linearly proportional then. So we call this the Bingham plastic fluid. Initially it behaves like solids. These are such fluids which behaves like a solids, but to a certain level of stress, when it exceeds that level, it behaves like a fluids. So there are some fluids which behave like a Bingham plastic. Sometime you will see some example, but sometime the for example the blood is also considered as, or sometimes jelly, when it behaves like a solid, while we applying the stresses, but when the stresses crosses the central limits, it deforms like Newtonian fluids. So we call the such fluids are uh, Bingham plastic fluids. Okay. So you can see again. Okay, this is very important table, and you have to draw this table, and you have to, from by using this table, you can you must be able to show the fluids. Okay, that which fluids are Newtonian, especially in non-Newtonians, and then in non-Newtonians we will have these because this is also non-Newtonian, this is also non-Newtonian. Okay, and also this behaves sometimes initially like non-Newtonian, but it behaves after applying the stress up to certain limit, it behaves like a Newtonian fluid. Okay, and um, from this figure you can see. Look at this one. As I have mentioned, this is the viscosity. So look at pseudoplastic fluids. In the pseudoplastic fluid, when the shear stress decreasing, or while you, this is your shear stress, when the shear stress is here, its viscosity is this one. Okay, and now you can see its deformation increases while increasing the stresses. Okay, so at this point you can see this is its viscosity, but if you increase the shear stress, viscosity is here. So there are some fluids, when we apply the stresses, Okay, this is the absolute viscosity, sorry, and this is the deformation. So with the deformation, you can see this is, look at this position, this is viscosity with this deformation. As the deformation increases, its viscosity decreases. Look at this one, and this is viscosity at this deformation, and this is viscosity at this deformation. It means, and look at this is viscosity. So the viscosity has decreased while decreasing the deformation. So when the fluid deforms and its viscosity decreasing, so though it is Newtonian fluids, so such Newtonian fluids will be called pseudoplastic. Okay, and look at this one. These are the fluids. When you are applying the stresses and deformation produces, so as the deformation increases, the viscosity increasing, it becomes more thicker and thicker. These fluids become thinner and thinner. Like in the pseudoplastic example, you can see the example of the paints. While when you apply the brush on the paints, when you apply the brush as a shear stresses, when you apply the brush to certain paints, it becomes thinner. So it means its viscosity decreasing. While there are some fluids, while you applying the brush or the stresses, it becomes thicker, and even it becomes solid after some time. Okay, we will have the example of such fluids. So such fluids are called dilated. I will discuss this one by one, okay, in the coming slides. So you must remember this graph when you say that uh, how you will describe the fluid, okay, from the diagram. So you will have this here, the shear stress tau, and here will be deformation, okay. This is du by dy. Look at this one, those fluid having this property. So this will be, look at the straight line, this viscosity is constant. So this here will be Newtonian fluid, okay, Newtonian fluids. But look at this one, some fluid will be here and maybe some fluid will be here, okay. And look at this one, some fluid, while you are applying the stress, will increasing the stress, no change will occur, no change will occur. Let me do from this one, okay, no change will occur. Maybe red one will work, okay. I am applying the stress but no change occurs, and suddenly when I reach the stress here, the fluids move like this. It is a straight line, not okay curve, which we call the Bingham plastic fluids, okay. So initially it behaves like solids. So all the fluids which is very near to this line, so it means it is more thicker. Remember, it is more thicker because, and those fluid which is lie at this very near to this line, these fluids are very thinner, okay, because its deformation is very, it deforms very easily, okay, at low stress. Look at the stresses here, the stress is here, but in this case look at the deformation is almost zero, and you can see the stresses are high. So at high stresses, if the deformation is low, so such fluids are more thicker, okay. And such those fluids which are here in this region where the stress is very small but it deforms, so we call this fluid as thinner fluids, okay. So this is the graph from which you can describe the fluids as a Newtonian and non-Newtonian, okay. So now what is the uh, and also we have defined the fluids like time dependent and uh, you can see this the time independent and time dependent fluids. So as we have generally described it, what fluids will be Newtonian and what fluids are non-Newtonians. Now we will discuss the type of the non-Newtonian fluids. Non-Newtonian fluids, as we said, do not obey the Newton law of viscosity. But there are some fluids. Now again, we further classified the non-Newtonian fluids as a time independent, which independent of time, like a pseudoplastic. Or we call this very simple shear thinning fluid. Shear thinning fluids. Okay, so uh, it does not depend on time, and we call this the shear thinning fluids. Non-Newtonian fluids for which the apparent viscosity eta, we have shown the apparent viscosity by eta, decreases with increasing the deformation rate. Okay, that Newtonian fluids for which the apparent viscosity decreases with the increasing deformation rate. Apparent viscosity decreasing with the increasing deformation rate. That is, for this we have n is less than 1. You can see in the graph we have uh, we are discussing these fluids. This is called the time independent pseudoplastic fluids. While increasing the viscosity, look at this is the viscosity. So while increasing the viscosity, okay, sorry, deformation, its viscosity decreasing. So look at this one, the viscosity, the deformation is increasing while the viscosity is decreasing, apparent viscosity is decreasing. So these are the pseudoplastic fluids for which we have the behavioral index is less than 1. Okay. Example of such fluids are polymer solution, colloidal suspensions. We call this microfluids. Some when we have like muds, some particles in the water, so we call this the colloidal suspension or microfluids. Some microfluids are inside the working fluids, and paper pulp in water. These are the example where the viscosity decreasing while deformation. Okay, we call this the shear thinning. Why we call this the shear thinning? When the shear stress is applying, its viscosity become thinner and thinner. I have given the example of the paints. All the paints behave like the shear thinning because when you apply the brush on uh, the paints, so it scattered. Okay, it means its viscosity becomes thinner and it's flow easily. And also we use some thinner also in the paints. You know this. And now the dilating or shear thickening, shear thickening fluids for which this the behavioral index is greater than n is greater than 1. If the apparent viscosity increases with the increasing deformation, while the deformation increases, okay, its viscosity also increasing, then the fluid will be in this category, in the category of shear thinning. It means you will see that normally we use that like when we use hammer, you know hammer, and you hit the fluid with hammer, and while you are hitting, after some time you will see that it becomes more thick. Okay, and maybe after a long time, after some time, it behaves like solid, so it becomes more thinner, thicker. So such fluids are called the shear thickening. Then after that, when you deform this, when your deformation or shear stress increases, it behaves like a solid. It is moving towards the solid. Okay, and we call this the cornstarch and sand. This is the example of the cornstarch, and even you can see. Sorry, this here you can see. Uh, if you look at this. Okay, then maybe you can see this in details at home. Okay, you just look at this uh, video. I have already provided this in your CLMS also. Okay, and even also it is given in you this slides. Skip this video again, and now you will comes. I don't know the. Maybe this will not incomplete in this range, but you can see, look at this, the viscosity of this
Classic
fluid.
Newtonian fluid is water. Water has a very predictable viscosity and will always flow predictably regardless of the forces acting on it. Newtonian fluids also have predictable viscosity changes in response to temperature and pressure changes. To investigate the properties of Newtonian fluids experimentally, let's start with some warm honey. As you can see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Even if we place a large force on it with a hammer, the honey predictably flows around the hammer. If we try the same thing with cold honey, we see, as you would expect, the honey is more viscous. That is, it flows slower. But when we test it with the ruler, we see it behaves much like the warm honey. It's the same when using the hammer. Applying a force has no effect on the viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid. Let's try a different fluid. We'll perform the same test with cornstarch solution.
Actually, this
When
is
you
a
pour
cornstarch
this
solution. Okay,
it appears to behave much the same way as the
look,
honey.
it is applying the stresses.
When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous. Hammering the fluid with even more force produces even more resistance to flow. Because a cornstarch solution's viscosity changes with an applied force, it is a non-Newtonian fluid. Unlike a Newtonian fluid, applying forces to this non-Newtonian fluid causes its particles to behave more like a solid. This makes the behavior of non-Newtonian fluids very strange. As you can see here, even though cornstarch solution flows when emptied from a bucket, you can't break its surface even when using a sledgehammer. You can even jump on and off a cornstarch solution. Just remember, don't stand on it, as you will eventually sink. So in summary, non-Newtonian fluids have unpredictable responses to applied forces. With applied forces, they become more viscous, such as cornstarch, or less viscous, like ketchup. What other fluids might you suspect to be non-Newtonian fluids?
Okay, so this is okay. So you can again you can watch this video, and now you will be able that how cornstarch is actually is a sheer thickening fluid. As by hammering, it becomes like a solid, and you can see the man was jumping on it, so it becomes very hard. Okay, so this is this such fluids, and you can see in the hands when after some time there was a material which was okay on which was held in both hands, and after some time it starts flow. Okay, it starts flow, so that is actually shear thinning fluids. So actually these are the fluids, the non-Newtonian fluids uh, uh, behaves unpredictably, okay, just like mentioned, uh, and sometimes its viscosity increase or decrease while applying the shear stresses. While in the case of Newtonian fluids, this is not the case. Okay, so now these are the ideal are being a plastic fluids, a fluid that behaves as a solid until a minimum yield stress exceeded and subsequently exhibits a linear relation between stress and rate of deformation. So uh, initially it behaves like a solid, as that is already mentioned in the diagrams where we have Newtonian, non-Newtonian fluids, and then it behaves like, look at this is just like the Newton law of viscosity. It behaves like a Newtonian fluids. Okay, so such fluids which behaves initially like a solid and then behaves like a Newtonian fluids are called non-Newtonian or Bingham plastic, non-Newtonian Bingham plastic fluids. And the example of this is drilling mud, toothpaste, and clay suspension. Okay, these are the example of the Bingham plastic fluids. Okay, so let me discuss these two. Uh, Time dependent fluids now. It depends on time, that after some times its viscosity increases or decreases. Before this, the fluids were independent of time. That if you keep the fluids in a container, and if you just to check the viscosity after some time without applying any stresses, so it will have the same viscosity, sorry, its nature will be remain the same. But there are some fluids which you call thexotropic fluids, fluids that show a decrease in apparent viscosity with time under constant applied stresses. Stresses are constant, you are applying the same stresses are constant, but after some time you will see that the fluid's viscosity decreasing. The fluid viscosity has been decreased, now it becomes thinner after some time. There are many paints, polymer solution, colloidal suspension, and people pulp in water, that when you keep it in a container and after some time, or even you apply the same stresses, okay, uh, okay, if you keep the stresses constant, but after some time you will see it be, such fluids become thinner and thinner. Okay, and then eupectic fluids, fluids that show an increase in apparent viscosity with time. That if you keep it in some container, and after some time you will see that it becomes thinner. So its apparent viscosity increases subject to a constant applied shear stress, like uh, gypsum paste, gypsum, okay, just like plastic pairs, that after some time it behaves like a is a liquid, but after some time it becomes like it changed to just like it shows like a concrete. Okay, so these are the different types of fluids which have discussed in these lectures, and I hope that you will be able now that if you have a fluid in your hand, if you have if there's a fluid in front of you, so you will be able to uh, to decide that the given fluid is Newtonian or non-Newtonian, and then in the non-Newtonian you will be able that the fluid is the being a plastic fluid, it is thexotropic fluids, it is pseudo-plastic fluids, it is eupectic fluids. Okay, so now you will. I hope that after this class you will be able to uh, to decide about the fluids, that the fluid is non-Newtonian or Newtonian, and also at the same time the different types of the non-Newtonian fluids. Okay. Again, if you have any ambiguity or queries about this lecture, so as we have already mentioned the time, so you can come, or even you can call me at the WhatsApp group. If you have any ambiguity, I will try to address your query. Okay, so thank you very much.